Now, the other thing you'll have to be able to do for these kind of problems is dilution calculations, which again, we did actually learn and use throughout this year, but learn last year.
Are there any more ice problems?
What's that?
Are we doing any more ice problems?
You'll see. Basically, it's the same concept as what we were doing in the last two chapters, but you're going to see it every time we've done one of these, every chapter we've done the ice problems you're talking about. It's gotten easier because there was something removed. Water was constant or whatever. You're going to see that this one's even easier too, as you'll when we get to the actual KSP, what that means. But for before, this is all still preliminary. None of that is necessary yet. To do those problems, you will have, what's going to happen is, if you think about, a minute ago I had up here, the last period, an equation like silver nitrate plus sodium chloride yields, or calcium chloride yields. Well, you're mixing two solutions together. When you do that, you automatically dilute them, as we saw in numerous labs. All right, if I took 20 milliliters of this guy and 20 milliliters of that guy, I'm diluting that one just by mixing the two together. They're no longer the molarity they were when you after you mixed them. So that's why we have to be able to do dilution calculations. All right, calculating the changes in the concentration when they're mixed, because that's what we'll be doing when we're figuring out precipitates. And again, we'll not just be able to predict whether a precipitate forms, but we'll be able to predict what the molarity has to be in order for that precipitate to be formed, and how many grams will be in that precipitate, or how many moles will be in that precipitate either. Whereas in the past, all we did was, this plus this yields that plus that, put a down arrow, and that was the precipitate. All right, you're going to be actually predicting the amount of it as well. All right, here's your equation for dilutions, though. Before we get to that, I'll do several dilution calculations, let you work on those problems, and then tomorrow we'll really be starting the actual chapter on solubility on KSP. All right, M1 and V1, M2 and M1 and M2 are the molarities, obviously. V1 and V. By the way, this doesn't just work for molarity. It could be any concentration, pretty much. You're going to dilute it. That's what's going to happen. If you know the concentration before and after, or volume before and after, you can solve for any one of the missing variables. Now, these are the kind of things that I do all the time in order to make up your solutions. You don't do them very often. There's a couple of labs I've made you do it in Chem 1 and maybe one in Chem 2, where you kind of had to do it. In this chapter, you'll have to do it because you're going to be mixing things together. But when I say I do it, I want you to look at this first example and you'll see what I mean. You you just saw that video on acids the other day. As we finish that up, I can't give you concentrated hydrochloric acid or concentrated sulfuric acid. You don't work with that for a lot of reasons. It would be very dangerous to have students, even college. I mean, you're going to be able to work with it, but it would be very dangerous to have students in high school working with that. So I make up from 18 molar sulfuric acid a weaker concentration that, if you spilled it on yourself, wouldn't immediately burn you. That's what you have at your table if we're using hydrochloric, or if we're using sulfuric, or if we're using anything. We generally have a dilute solution of it so that you don't kill yourself. So I have to mix them up. Now, I'm at the point where I just make up certain stock solutions, and I know how much to add just off the top of my head. I don't even have to do the calculations. You can take that down? Let's go to the back. You can use one of those tables.
All right.
Actually, no, just sit at one of the desks back here. Because all right. So I have in the back of the room, back in the stock room, 18 molar sulfuric acid, but I need 0.90 molar sulfuric acid. I have to know how to make that. All right. And I need, for the lab, I know I'm going to need about 1.5 liters of it. So this is the kind of stuff I have to do all the time. Again, I don't normally, because I'll make up a big bottle of something and I'll keep it around for months or even a year, because it's not going to go bad. It's hydrochloric acid. So I'll make up. Usually I don't do this calculation every time, but in my head I am. All right. So M1, V1, M2, V2. Oh, by the way, as I think I mentioned last year when we covered this, you will not do that. You won't have the advantages you've had here in high school. You're not going to, most labs that I recall doing, there was not at my table the exact concentration I needed for that lab. I had to go to the stock room, and I'm not just saying like, oh, wow, I had to do it. I mean, everybody had to do it, and you all will have to do it. Go get the stock bottle, dilute it, or get the solid, for example. You have done this. Sodium hydroxide, I make it up a base solution. You get my sodium hydroxide, the solid, I mix it with a certain amount of water, and that it will give me the concentration I'm looking for. So you have to make those up on your own. That's why labs in college take 2 to 3 hours, whereas we try to shove them into either 45 minutes or a single period or an hour and a half. All right, so my M1. You have to read these questions because it's not always listed in order, as you'll see in some of the other examples. But this is my initial concentration, 18.0 molar. And it wants to know how many milliliters of that I need. Now you must look at how many milliliters of this. So that's my V1. That's my unknown. And I want to make this concentration 0.900 molar. And I need about 1.40 liters of it. By the way, even when I'm done with this problem, there's something else you have to realize, and that is how you're going to make it, the actual procedure you would use to make it. And there's 2 things to remind you about that. All right, M1 V1 equals M2 V2. I'm solving for V1, so I'll divide both sides by M1. V1 is going to equal M2 V2 over M1. M2 is 0.900 molar. V2 is 1.40 liters. And M1 is 18.0 molar. Point oh 700.
Yep. That's
liters.
though.
Right. I was just saying. I thought it was. There, I did the same problem. I must have used different numbers. I thought it was 067, but it's 0700.
Yeah.
Okay. All right. Okay. That's molars canceled. Leaves you with liters. Now that, of course, is in liters. So if I'm doing this, now here's my next 2 questions. Even when you get that, that's all you have to do for the problem. That's the answer. But we have a lab back there. We're going to be doing. All right. When we're doing a precipitate lab, you're going to have to mix up these solutions and dilute them and do this stuff with them. All right. You have to know what to do now. What does that mean? That means you got to get this many liters, which would be basically, how many milliliters would that be? 1, 2, 3, 70 milliliters. And I would add that. Now, there's 2 things. Would I add that to 1.4 liters of water? Would I add it to 1.4 liters of water? No. I'd have to add it to what? 1.4 liters minus 70 milliliters, right? Because its total volume has to be 1.40 liters, right? So it would be, 1,330, right? Is that right? Number 2, I can't just say, well, I'll put the acid in first, and then I'll fill it up to the 1.40 liter mark. Why not? Say, well, it'll work concentration-wise. That would give you the correct answer. But why can't I just have my big beaker, put my 70 milliliters of concentrated sulfuric acid, and then pour in the rest of it with water? What will happen? It'll react. The water, when it hits that concentrated, you never add water to acid. You may remember from the video we saw. If you add water to acid, it will splash up at you. All right, because it gets very, very hot. All right, so you always add acid to water, never water to acid. Because as I add the acid, if this was this much water in here, and I'm adding acid to it, it has a chance to dilute and disperse the heat. So there's 2 things you have to realize when you're doing that. You always have to add the acid to the water, and your total volume has to be 1.40 liters. Okay. All right. Now let's do a couple more examples. This one here. Determine a new concentration at 50 milliliters. And this is the kind of stuff you'll be doing in the labs, guaranteed. $50 milliliters of 4.0 molar HCl are added to 50 milliliters of water. That is a really good mistake to make here, as you'll see. Very common mistake. M1, V1, M2, V2. Very common mistake made here when we go just picking out the information. My first molarity, read it. Read what it says. Everybody agree that's 4.0 molar, right? And everybody agree the initial volume you have is 50 milliliters. My new molarity, well, that's easy enough too. What's that? Determine the new concentration. Okay, that's the unknown. And V2 is 50.0 milliliters, right? I made the mistake. You didn't see it. So that's what's going to happen. What's the new volume?
100.
It's 100. Right. It's not 50. All right. And that's the mistake you'll make. Just reading off the numbers, that's what you'll do. But it's going to be 100 because that's your new volume. You may remember doing this in a couple of labs already where we had to do multiple dilutions, the test tubes and all that stuff. We had to always keep in track of the initial volume you had and then the new volume after you've mixed it. We did that in at least 2 or 3 Chem 2 labs, not to mention we originally learned it in Chem 1. Now, did I give you this equation at that time? I think I might have for one of the labs, but that's just how you diluted it. And then we used the computer, the spreadsheet to do the dilutions of the airtime. All right, M1V1 equals M2V2. My M2 is what I'm looking for this time, so I'll divide both sides by V2. So M2 equals M1V1 over V2, which is 4.0 molar times 50.0 milliliters. By the way, I also did this one for a second reason, over 100 milliliters. And basically, what do I get? 2.0. Now that I've got that answer, it should be obvious why we should have known this answer before we even started the problem. And again, it's the real reason I did this, to show you why equations look the way they do. Everybody should have known just reading this problem that if I took 4 molar, 50 milliliters of it, and I added 50 milliliters of water to it, I'm going to cut the concentration in half. Everybody probably figured that out on their own. All right? But here's why it works. Here's why the equation looks like it does. Look what you're doing. To find the new concentration, you take the old concentration and you multiply it by the factor, the fraction by which it changes. 50 over 100. The old volume over the new total volume is 1/2. You're basically multiplying by 1/2. That's why it works. All right. So again, you see equations in chemistry aren't just there, and they're not there for any science. They're not just there because that's what they came up with. I always get that kind of a question. Well, where do they come up? How do they come up with this stupid equation, or how do they come up with this stupid idea? It's not that. It's just it's just the way it is. It works. That's why it looks like it does. All right. Last one. How much water do you need to add to 3 liters of 1.40 molar salt solution diluted to 0.80 mole? This is working a different direction. Here I'm being asked the volume you need. But if you look at it and you try this one on your own, you realize that it's not any different. You're using the same exact equation. You're solving for a different variable. You will have to, again, at the end, make sure you understand what it is you would do to make this solution. It's not exactly, just looking at the number at the end. That may be the answer, but you have to do something to it when you're in the lab, actually how you do it. So basically M1, V1, M2, V2, my initial molarity, 1.40 molar. My initial volume, what does it say? That's my initial molarity, and I have 3 liters of it. So what's my initial volume? 3. It's not my unknown. The unknown is how much water do I need. Okay, so what's the new volume going to be? And even that won't be the actual answer, as you'll see. M2, 0.8, that's what I'm trying to make. 0.80 molar, and I want to know how much water I need to add to it. Actually, I need that V2 is not how much water needed to add, but rather how much it will need to be at the end, which we'll see. All right, M1 V1 equals M2 V2. I need to solve for V2, so I'll divide both sides by M2. So V2 equals M1 V1 over M2, which is 1.40 molar times V1, which is 3.0 liters, over M2, which is 0.800 molar. Now, what do you get for that answer? 5.25 liters.
But you're only adding.
Right. As I say, that is not the answer. That is the answer you get to the calculation. But this shows you, again, fundamental misunderstanding of the problem if that's what you circle as your final answer. Okay, the question didn't ask me, what's the new volume going to be? The question asked me, how much water do I need to add to 3 liters? That's what the new volume has to be. So what are you going to do with those two numbers? Subtract. 5.25 liters minus 3.0 liters gives you 2.25? 2.25 liters. That's your final answer. That's how much water you would need, all right, to make the new volume add up to 5.25. Okay, that's what the V2 means in this case. I think that's the last one on these, and I have more problems to do. All right. Those are the homework problems. They are all dilutions. You'll be solving for M1, V1, and M2, V2, one or the other in those.